This is the test prep for test number 3. So technically this is actually the third test review that you guys have had for this particular test. So let's go through these, and I feel pretty confident you'll see items of this nature on your upcoming test. Number 1, I'm looking at a limit statement, and it looks very much like a derivative. So it's not just a ordinary limit, it looks like it's going to be a derivative, and the format that it looks like I'm looking at is the limit as x approaches c of f of x minus f of c over x minus c. That is the format that it looks like. Now I'm going to have to double check that, because if this is the case, then f of x, the function, is 3x minus 4. But before I make that final decision, I need to make sure, that was a c right there, x is c. I need to make sure that f of 3 actually generates 5. That's my question. So when I substitute 3 in place of x, I get 3 times 3 is 9. 9 minus 4 is 5. So I have verified that this is actually the f of c value. So now I figured out that this is asking me for the derivative of f of x. So it wants f prime of x evaluated at 3. Well, if the function is 3x minus 4, the derivative of 3x minus 4 is 3 all the time, because 3x minus 4 is linear. So the derivative at 3, the answer to that is simply 3. So that's what I would select for my answer, and then this is just an explanation of what I just told you. This statement is the definition of derivative of this particular format. Number 2 also looks like I am possibly looking at definition of derivative, but it could be just an ordinary limit. The second question over here on the right side, to me, looks like I'm looking at the limit as h approaches 0 of f of, now right here it looks like it's point specific, c plus h minus f of c over h. So that looks like the well, there are two forms of the point-specific derivative, and you guys should be able to identify that. Now, if I'm right, then I would say that f of x is equal to 4x cubed minus x plus 1. And then I want to substitute my c value. I suspect that c is negative 2. What I want to check is to make sure that this is actually f of c, and that this actually is a derivative and not just an ordinary limit. So I'm going to substitute negative 2 in place of x minus negative 2. Be careful with those negatives. They can really mess you up. Negative 2 cubed is negative 8 times 4 is negative 32. Plus 2 plus 1, and then negative 32 plus 3 is negative 29, and that confirms, because there's a plus, minus negative 29 makes a plus 29. So now I know that this expression wants the derivative of f of x, so f prime of x is equal to 12x squared minus 1, evaluated at negative 2 would give me 12 times negative 2 squared, so that's 4 times 12 is 48, minus 1 is 47. So this entire expression simplifies to be, there we go, 47. And again, this is an explanation of what I just told you in the video. All right, moving on, let's slide the screen down to number 3. In number 3, we have a position function. This function represents the position of a particle, and the units for the particle movement are miles, and the time is measured in hours. Letter A, determine the acceleration of the particle when it is at rest. So there are two things going on here, and reading is going to be very important. So really, the first thing I need to figure out is not the acceleration. The first thing I need to figure out is when is the particle at rest, and then the second thing I need to figure out is what is the acceleration. Now, when the particle is at rest, we've talked about in class, that means the velocity is equal to 0. So job 1 is to figure out when velocity is equal to 0. So I'm going to I'm going to determine the velocity function by taking the derivative of position. So v of t, using the power rule, is 12t squared plus 13t, just using the power rule, minus 35. That is my velocity function. I'm going to set that equal to 0, and I'm going to need to factor that. So factors of 12, I'm going to try 3 and 4, and the factors of 35 are 7, so I'm going to do a, let's see, 7 and that would be 28, 15, so it looks like a 7 and a 5, because that would give me 28, and that would give me 15. That would give me a 13 in the middle, and I want a positive 13, so I'm going to need the 28 to be positive and the 15 to be negative. So when I solve each of those by setting each factor equal to 0, I get t equal to negative 7 over 3. And this problem tells me that time is valid for greater than or equal to 0, so nothing comes out of this. And I get t equal to 5 over 4. So this is when the particle is at rest. Now, the next part of the problem said find the acceleration at that time. So I'm going to take the derivative of velocity using the power rule, and that gives me 24t plus 13, and I'm going to substitute 5 over 4. So the acceleration, 24, 5/4 plus 13. 4 divided into 24 is 6. 6 times 5 is 30. 30 plus 13 is 43. This is acceleration, so that would be miles per hour squared. So that's what we're looking for in 3A. And my work will confirm, except for my units. Wow, I noticed that those units are not correct, so let's fix those to make that miles per hour squared. Letter B, using the same information, find the velocity of the particle. So we already have, back over here, we already have the velocity function right here. When the acceleration is 61 miles per hour. So job number 1 in this case is to figure out when is the acceleration 61 miles per hour. That's job 1. And then job 2 is to find the acceleration. So I'm going to find when the acceleration, so I'm going to take the acceleration function, 24t plus 13, set that equal to 0, subtract 13 from both sides and divide by 24. So that's the time when the acceleration is, oh no, it said 61 miles per hour, not 0, sorry. Let's fix that. Okay, so we're going to do the same thing. We're going to subtract 13 from both sides, which gives me 48. Divide both sides by 24, and t is equal to 2. All right, I'm going to substitute the time of 2, because that's when the acceleration is 61 miles per hour square. I'm going to substitute that into velocity, and that will give me 12 times 2 squared plus 13 times 2 minus 35, which gives me 2 squared is 4 times 12 is 48 plus 26 minus 35. And that gives, whoa, and that gives me 39. This is velocity miles per hour. And when I do my reveal, it's going to say the same thing here. So you can see this work posted in our shared Google folder, but I wanted you to here be able to see the explanations of what's going on. So I'm going to clear the screen and start with number 4. So let me slide this down just a little bit. All right, so number 4. In number 4, we're going to do some symbolic representation. So this time we're not actually going to have to do the work. We're going to set up how to do the work. And so is that still linked to, yes. Yeah. So we are going to have to, I guess, sort of assume that since we're talking about average acceleration displacement, so we're going to talk about S of t being our generic position function, and then S prime of t, which is v of t, being our velocity function, and the second derivative of position is the first derivative of velocity, which is acceleration. So those are our 3 functions that we're going to use their names generically. So in letter C, 4C, we are looking for the average. Look at your keywords, average acceleration. So A is average, which reminds me of Algebra 1. So when we deal with slope in Algebra 1, well, slope anywhere, but our Algebra 1 formula for slope is y2 minus y1 over x2 minus x1. So that's what I'm trying to produce here. But I want the average acceleration. Now, we've talked about this many, oh, there's an I missing there. We've talked about this many times. Average acceleration is not, it's not the change in acceleration over change in time. You have to go back to the velocity. So what we're looking for the average acceleration is change in velocity over change in time. And we've also talked about in class that when you are not sure, so let me write this down here. So here's v of 5 minus v of 2 over 5 minus 2. If you want to make sure that you have the right thing, you do a units analysis. So in this problem, you would ask yourself, all right, so I'm going to do this. Question, what units is velocity being measured in this setup? Well, velocity is being measured in miles per hour. So that's my numerator. So that goes here. What are the units of the time in this problem? Those are hours. So if I do, it might be easier if I write this a little differently. We don't normally write miles per hour this way, but I'm going to do it just for an emphasis. So really, this is miles per hour divided by hour over 1. So if we multiply by the reciprocal, we would get miles per hour times 1 over hours, which is miles per hour squared. That confirms that we have the acceleration because we know that those are that miles per hour squared are the units of acceleration. So I started to say, are there any questions? But I guess there's no one here, right? All right, so let's go to letter D. Displacement. D for displacement. We have discussed in class the definition of displacement. And in case you don't remember, the definition of displacement literally is change in position, or change in position, or terminal position minus initial position. Remember, subtraction indicates change. If you go to the grocery store and you give them more money than your item costs, they give you change. How does the cash register determine that? It subtracts what you gave minus what you owe. So subtraction is your change. So terminal position minus initial position gives you displacement. So in this case, terminal position at 5 minus position at 2, and position is measured in miles. That would be your displacement. Letter E sort of is a throwback to letter C, same idea. So we have average and average. So we're talking y2 minus y1 over x2 minus x1, but you have to get the correct y. So just like we said before, for average velocity, it's not change in velocity. You have to go back to position. The definition of average velocity is change in position over change in time, and you can do that unit analysis again that I showed you a minute ago to confirm that you have done the right thing. Number 5, now we're getting onto a velocity graph. So every time you have a question here, you have to ask yourself, how does this question relate to velocity? So in letter A, I want to have a conversation or give an answer about acceleration. So here's my brain work over here. What's the relationship between acceleration and velocity? So in my brain, I have to know that acceleration is the instant, here's my keyword, slope of velocity, which means I need to investigate slopes of velocity. And I'm looking for the slope of the tangent lines to be negative. So then I ask myself, well, acceleration is instant slope of velocity. I want negative slope. What would velocity graph be doing for negative slope? Well, the velocity graph would have to decrease. So I am looking on the graph where the velocity function decreases. So down, 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 decreases down. Decrease, 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 decrease. So on these two intervals here and here, the velocity graph decreases, therefore the slopes of the tangent lines are negative. So we're going to say acceleration is negative on the interval from 0 to 2. If I can get that to go in the trash can and slide it back up. On the interval from 0 to 2, and on the interval from, that 5 should be an open, not a close, so let's fix that. 5 to 10, because velocity, and look at my justification, velocity is decreasing. Let's clear the board and go to the next thought. So we're still dealing with acceleration. This time we're asking, what is the acceleration at t equal to 5 seconds? So we already had that conversation. Let me select my pen. We already had the conversation that acceleration is slope of velocity. So another way to interpret this question right here is, when is the slope of velocity, what is the slope of velocity at t equal to 5? If you don't do the brain work over here on the side, you're likely going to make a mistake. Acceleration at 5 seconds. So I'm going to come over here to my graph. I'm going to go to 5 and whoa. So I noticed that at t equal to 5 seconds, v of t is not differentiable, because the left and right derivatives do not agree with each other. So we cannot determine the acceleration at t equal to 5 seconds because there is no derivative at that time. And then notice my beautiful, beautiful write-up. The acceleration is not defined at t equal to 5 because v of t is not differentiable. And then I wrote up that the left derivative does not equal to the right derivative. Letter C. In letter C, the key, you make sure you read. We are looking for, get a pen, get an orange. We are looking for particle, this one's tricky. Particle moving to the left. So that's one thing I have to pay attention to. Speeding up is another thing I have to pay attention to. So idea number 1 is when is the particle moving to the left, and idea number 2 is speed up. Okay, so first of all, let's identify when the particle is moving to the left. Remember, we can use velocity to determine particle movement. We're going to consider the sign. And if we want the particle moving to the left, then we're going to need negative velocity, where the velocity is negative, not decreasing. That's not the same thing. So the velocity is negative when the graph is below the x-axis. So velocity is negative in the orange region that I'm coloring right here. Velocity negative, velocity negative, velocity negative. All right, so in that region, I have figured out where the velocity is negative, but I'm not done. The next thing I need to figure out is when is the particle speeding up. Now for speeding up, I can simply do, we know that speed is not acceleration, but in fact speed is the absolute value of velocity. It is velocity without considering the sign. It's just how fast the particle is going. So what I can do is I can actually take the absolute value of this graph. This goes to a low of -4, so it'll come up here. And I can basically reflect the graph upward. And now I can see the particle is speeding up from 0 to 2, and the particle is slowing down because now I have a speed graph instead of just a velocity graph. So this region right here is the speed up region, which corresponds to this region down here. So now I know the particle is moving to the left and speeding up from 0 to 2. Let's do the great reveal. And so notice what I have here. 0 to 2, because first v of t is negative. That is where the particle is moving to the left, and v of t and a of t both have the same sign. That's not something that we've talked too much about yet, but might as well throw this in here while you're learning. So another way that we can get speed, write this down and hold it because we will come back to this again. When I want to know speed up versus slow down, which is they're both components of speed. This is another true statement about speed. When v of t, velocity, and a of t, acceleration, have the same sign. In other words, velocity and acceleration are both positive, or velocity and acceleration are both negative, the particle speeds up. I'm going to give you the second statement and I'll show you what I'm talking about in this case. Second statement, when velocity, v of t, and acceleration, a of t, have opposite signs, it doesn't matter how they're opposite, doesn't matter which one's positive and which one's negative, the particle is slowing down. And the nice thing about knowing these two statements is we don't have to create a speed graph, and perhaps there may be a situation where we don't even have the graph and could not create a speed graph. So let me erase this and just kind of show you how this works. So in this case, we wanted to know when the particle is moving left and speeding up. So remember, we had already identified moving left, velocity negative, so moving left was in this orange zone, so I'll put that back. All right, now, in this case, for speeding up, which is right here, come over here to the two sentences. We said particle speeds up when velocity and acceleration have the same sign. So in this first region, right here, the velocity, we already know the velocity is negative, but since velocity is decreasing, the slopes of the tangent lines would be negative, therefore acceleration is negative, versus on the other side, the slopes of the tangent lines, this is terrible, the slopes of the tangent line are positive, so velocity is negative in this region, acceleration is positive, so the particle is slowing down. So same sign of velocity and acceleration, we're speeding up. So just kind of stick that away. You will be using that. Letter D. What is the speed of the object at 3 seconds? So I'm going to clear my annotations. There we go. Speed at 3 seconds. So I'm going to come over here to the graph. 1, 2, 3. I'm going to come down here. Now I know V of negative, V of 3 is negative 3. But I'm not interested in velocity, I'm interested in speed. So I want the absolute value of V of 3, which in this case is the absolute value of negative 3, which is 3. Did I have any units on this thing? I don't see. Oh, yes, I do. 3 feet per second is the speed at 3 seconds. Letter E. Whoa, I just sent you guys an email this morning about interpreting a derivative. So, letter E, in the context of the problem, interpret what S prime, or V of 2, equals negative 4, indicates about the position of the object. So remember the conversations that we've had is that a derivative reveals, shares, provides, modifies the preceding function. So in this case, since you know that V of 2 is equal to negative 4, this is going to be a descriptor of the preceding functions. This is going to tell me about position. The next thing I'm going to consider is that the velocity is negative, so the position increases. So let's see what we got. 5-point question. We begin with at what time? At 2 seconds, the particle is moving to the left. So the subject of my sentence is particle movement and what is the particle doing? Moving to the left at a rate of 4 feet per second because the velocity is negative. Interpreting a derivative. Letter F. Here's another one. In the context of the problem, what does V prime of 8, derivative of velocity or acceleration at 8, indicate about velocity? So we're basically going to follow the same pattern at 8 seconds. So acceleration modifies, describes, indicates information about the preceding function. So acceleration tells me whether velocity is increasing or decreasing. Since the sign of acceleration is negative, the velocity will be decreasing. At 8 seconds, the velocity is decreasing at a rate of 1 foot per second squared because the acceleration is negative. And that's it for the test. Let's see if I don't think else in here. That's it for the test prep items. So guys, this is basically your third review. You should be really, really ready for this test.